Hello, my name is Gianna Lee, and I will talk about the motion of a falling object. First, I will introduce the purpose and procedure, and then discuss the observational and computational models, followed by a comparison, and finally conclude with my findings and further understanding. The purpose is to observe the effects of gravity and drag force on an object dropped from rest. To do so, we will create an experiment, model the experiment, and compare and contrast results. Some fundamental physics principles for this lab include Newton's second law when F net is not zero, and gravity and drag force. Newton's second law will be represented via the velocity update formula. Gravitational force on Earth is equal to mass times acceleration g in the negative y hat direction. And finally, the drag force is equal to negative b times the absolute value of velocity squared times v hat, where v is a proportionality constant, and absolute value of velocity is speed, and v hat is the direction of velocity. In the experimental model, a balled-up paper ball was observed in tracker where the system was the ball and the surroundings was everything around it, like the air, floor, and my hand. For the initial conditions, the velocity was 0 and the position was 1 meter in the positive y direction, and it took about 0.533 seconds to reach the floor. Using the information from the tracker software, one can see that the position of the ball with respect to the y-axis gradually decreased over time. In GlowScript, a computational model was created to represent the experimental model, one including drag force and another without. The mass of the object was about 0.005 kilograms, and the time step from the tracker was about 0.033 seconds, which was our delta t. In the while loop, we only measured the gravitational force, and the resulting graph shows the object's position slowly decreasing over time while the acceleration remains constant. Comparing the experimental model to the computational model, it is clear that the position of the ball changes quicker in the computational model, while the velocity of the object in the experimental model slowed down over time. To account for this, the second computational model includes a drag force in the F net equation. The new graph shows that the velocity of the object isn't constant. Now, comparing both computational models, it is evident that the net force, including the drag force, is a more accurate representation. Discrepancies between the computational and the experimental model also include human error with tracking the object in the tracker software. For further understanding of the object, do any of the models predict a terminal velocity? Yes, the computational model that includes a drag force predicts that the object will stop accelerating and reach a terminal velocity in which it cannot exceed. And what if the ball was initially thrown with a downward force? The acceleration of the ball would still decrease as it would still be acted on by the same net force once in motion. The difference, however, might be that the changes to the velocity and acceleration are faster. To conclude, the effects of gravity and drag force cause a falling object's velocity to slow down and reach a constant terminal velocity. And when only gravitational force is present, the acceleration remains constant. Thank you for watching.